So here we are on part one of alkyl halides nucleophilic substitution reactions. And in substitution reactions, what we have is we have a nucleophile, which we've talked about in the past, and an electrophile. And the nucleophile in the mechanism ends up attacking the electrophile and kicking out the leaving group. Leaving groups are anything that leaves as a weak base. So all good leaving groups must be weak bases, and the leaving groups we'll start with are the chloride, the bromide, and the iodide. They're all good leaving groups because they are weak bases, because they're the conjugate base of a strong acid, HCl, HBr, and HI. So how do we name an alkyl halide? Well, first we have to identify the parent chain. So in the example below, we can look and see that the longest carbon chain is that right there. And then we need to identify the substituents. We have two of these methyls, and then we also have one bromine. So we have to get all of that included in the name. So when we have a halogen, it is a substituent that ends in O, fluoro, chloro, bromo, or iodo. And so our example here would be if we number the chain so that we get the substituents to have the lowest number possible, we see that we have a 2-bromo and a 2-methyl, but we also have this 5-methyl, so it'd be 2-bromo, 2,5-dimethyl, and then since it's 7 carbons, it's a heptane. So try naming these two on this page. I'll give you a second to work, and then we'll talk about them and see if we all agree. Okay, so on the first one, we see that the longest carbon chain are these 5 carbons. So off of it, we have a bromine on carbon 2 and a methyl on carbon 3 if we number this way. So that's the lowest possible number. So it's going to be a 2-bromo, 3-methyl pentane. And the next one, if we have an alcohol, we drop the E and add OL because it's an alcohol. Alcohols end in OL. So here we number the chain, or figure out the longest carbon chain. It's these 5. 1, 2, 3, 4, 5. So on that 5 carbon chain, it is some substituted pentane, but we drop the E and add OL. So it's a pentanol. The alcohol is on carbon 2, so it is 2-pentanol. And then out in front of all of that, it has a 3,4-dimethyl 2-pentanol. So the next thing we have is primary, secondary, and tertiary substituents. If we have like a bromine or a halogen on a carbon, if there is one other carbon on it, it is a primary halogen. A secondary halogen or secondary leaving group has 2 R groups on it, and a tertiary has 3 R groups on it. And that'll come into play more as we go through this chapter. So there are 2 possible ways to do a substitution. The first thing we can do is we can substitute a halogen for a hydrogen and the free radical process. And there are 6 different patterns for a radical reaction. First, we have the homolytic cleavage. This is the initiation. This is the first step of every free radical process. And it has 2 electrons that have to move, so it'll always have 2 arrows in that step. The next one, or the next 4, all have 3 electrons moving, We have the addition to a double bond, hydrogen abstraction, halogen abstraction, and the elimination reaction. And these are the four basic propagation steps. And in a propagation step, you see each one of them had 3 electrons that had to move, so we have to draw 3 arrows for this. And then the last type of step is the coupling reaction, or the termination. And in the termination step, it is just like the initiation, in that 2 electrons have to move as we're going along. So we have to draw 2 arrows in that. And all free radical mechanisms will be the same. We have to be careful what type of arrow we draw, just like we've talked in the past. Since we're moving 1 electron at a time, we have to draw the fishhook arrow with just 1 hook on it, not 2 as we've been drawing for all our other reactions. So here we have the mechanism for the reaction of adding the chlorine onto methane, where first we have the initiation, where the chlorine bond splits apart to form 2 Cl radicals. The Cl radical will pull a hydrogen off of the methane to form a new free radical. So in any propagation step, we have a free radical and a small hole molecule. In propagation step number 2, we have a free radical and a small hole molecule. And these react to form a new free radical and a new small hole molecule in each of the propagation steps. And then in the termination, any 2 free radicals can form a bond. And I tell my class that any free radical that you have legally formed in that mechanism can come together in the termination step. All products in a free radical process must be formed in a propagation step. So you have to show enough propagation steps to form both products. And be careful about the free radical process, because we only do a few of them throughout organic chemistry, not a bunch. Most of the time we'll draw the regular mechanism. So initiators for this are normally either bromine halogen bond and a peroxide, or the peracid, peranhydride, and these all have the same sort of bond that we can homolytically cleave to start the process along. So in this, there are 2 possible products. If we started with propane, there are 2 possible products that we can form, where we have the 6 hydrogens that are primary and 2 that are secondary. And with the halogen, with chlorine, when we try to halogenate the propane, we get a 60-40 mix of the 2 possible compounds based on how reactive the 2 positions are and how many hydrogens we have. If we get into the bromination, bromine is much more selective for the more substituted carbon, so we don't have to worry as much about it. And with propane, we get a 97-3 ratio of products when we brominate propane. And that's just because of the stability of the free radical that we've talked about in the past. The more substituted a free radical is, the more stable it is. So the secondary radical is much more stable than the primary radical, and in the bromination reaction, it favors the more stable free radical very highly. If we go down to the bottom of the page here and compare isobutane, butane, and either the chlorination or the bromination of it, we see that the tertiary bromide is formed in 100% versus the primary, whereas the tertiary chloride is a 72-28 ratio. So the bromination is a much cleaner reaction and much more favored for doing a halogenation reaction of an alkane. One reaction that we can accomplish pretty cleanly is the allylic bromination, and what we need is to have an allylic hydrogen, which is a hydrogen on the carbon next to a carbon-carbon double bond, and the first propagation step or the initiation for this, as we've said all along, is the splitting of the bromines to form the bromine free radical. So this is our initiation. And then in our propagation steps, we need to go far enough that we form our products. So in our first propagation step, we remove the hydrogen to form HBr. This free radical we know is very stable because we can draw resonance structures for it. Let me redraw it. And the more stable something is, the more resonance structures we can draw, the more stable it becomes. So we can draw this, the resonance structure for it, and then in the second propagation step, we can have this free radical. In this example, it doesn't matter which one because they are equivalent. It'll grab a bromine off of Br2 to form our other product, along with some bromine free radical. And then in the termination step, we can have two bromines come together. And as I said in the last slide, it doesn't matter what two free radicals come together. We could bring two of the cyclohexenyl free radicals. We could form a bromine and a cyclohexenyl free radical. It's up to you what you want to draw. The easiest one is reforming whatever initiated the reaction. So the two things we can do with the double bond is we can have an ionic reaction where the double bond goes out and attacks the electrophile. This would form the cation, and then Br minus could add to that to give us our product, where the bromine added to the more substituted carbon. And that's when we just have HBr. If we have HBr and a peroxide, the peroxide is going to be our initiator, initiating the reaction to form two RO radicals. In our first propagation step, the RO radical will abstract a hydrogen off of HBr to form ROH plus bromine free radical, and then the bromine free radical in the second propagation step can react with the cyclohexene, and as we learned a long time ago, the more substituted a free radical is, the more stable it is. So we want to add it to the carbon, so we form the tertiary free radical. Then this tertiary free radical in the next propagation step can abstract a hydrogen off of HBr to form, lost my bromine, our product, where we added a hydrogen on the more substituted carbon, and then we terminate the reaction with two free radicals coming together to form Br2. Okay. Or we could have two RO free radicals coming together to reform that. It doesn't matter what the termination step is. But the comparison between these two reactions, while one puts the bromine on the more substituted carbon. That is where you form the cation, and the Br minus adds to that cation. We know carbocations, the more substituted they are, the more stable they are. So if we have the opportunity to form the more stable cation, our nucleophile will add to that carbon. And so the intermediate tells us which way the reaction goes. In the second reaction, where we have the free radical, we all know that the free radical is just like a cation. It's electron poor. So the more substituted it is, the more stable it is, and then it will go grab a hydrogen off of our HBr to form our product. So it's all about that intermediate that tells us what can happen, and you don't have to worry about is it Markovnikov or anti-Markovnikov. That's a name I will not say in class, just because it doesn't help out any if you memorize everything. So here we could coronate cyclohexane and it doesn't matter because we get all of the same products. But in the next one, we have a tertiary hydrogen. So Br2 will initiate the process to form two bromine free radicals. The bromine free radical will react with the 3-methyl pentane to abstract a hydrogen off of the tertiary carbon to give us HBr, along with the new free radical. This free radical can react with Br2 to abstract a bromine off of it to form our second product, along with bromine free radical. And then in our termination, the bromine free radical can react with another bromine free radical to form Br2. And there we have the bromination for the 3-bromo 3-methyl pentane. So the bromination of an alkane is of limited synthetic utility. It has to be used on an alkane. It needs to have a difference in reactivity for one carbon, and it's best if it's bromine is the reagent we use. So we can brominate it to add the bromine on the most substituted carbon, and then from there we can get into both the substitution and the elimination that we will continue on with in this section.